Hello class, welcome to the part 2 of this module, which is just discussing more examples on two-sample hypothesis testing. We're going to have z-test, z-test on proportion, and t-test with separate variance. On to the next sample. And again, if you would like to understand the problem thoroughly, just pause the video. I will just run you through the problem because I might hit the 15-minute mark on YouTube. Anyway, hunt for the clues first. What's the sample size? According to this problem, it's 50. That's more than 30. Then this statement means the parameter that we have is average. Okay, average tensile strength. Now it's obvious that this problem requires a hypothesis testing of z-test. That is according to the conditions. So always review the conditions that you have. Step 1, identify the hypothesis. The null hypothesis is that the difference between their average would be 12, but the manufacturer claims it is more than that, with thread A exceeding thread B, so that means thread A would be bigger than thread B, so that goes first in the expression. So we're going to write the alternative hypothesis this way. Mu A minus mu B is greater than 12. The operator is obviously greater than sign, making the study a right tail. Step 2. Identify the level of significance, which is 0.05. The tail is right, and then the n is 50. But since this is a z-test, we don't really need to look for the degrees of freedom. How so? Well, z-test uses the standard normal distribution, which does not change no matter the sample size. We need it in t-test because our sample size is so small that it only approximately follows the standard normal distribution. So we have to include it in the critical value. And that is why we need the degrees of freedom, which is n minus 1. You may see it as a consideration to give space for the freedom, knowing that our value could never be as accurate as z-test. Well, I just want you to know the theories behind it. You may search more source materials for longer and more detailed explanation, but that is the simplest way I can discuss it. Going back, we don't need the degrees of freedom in z-test. Sample size is large enough, and our critical value is 1.645. There. Step 4 is sketching it. Our sketch will be on the right-tailed, and the score starts at 1.645. Step 5 is solving the standardized test statistic, and since the z formula is more straightforward, it is easier to solve. By the way, notice the cancel part here. Mu1 minus mu2. They are unknown population parameters. We know x bar 1 and x bar 2, that's 86.7 and 77.8. Okay, we know them. They are the sample mean, and they are way different from the population mean. That is why I mentioned that the sample statistic and population parameter are distinct here. We do not know what our mu1 and mu2 are because they are theoretical numbers. These are the things that we only assume, but we know that whatever they are, their difference is 12. So we replace that whole expression with 12. Going back, the standardized test statistic is negative 2.6. That is way lesser than the positive 1.645 that we have. And that means we do not reject the null hypothesis that states that there is no significant evidence to prove that their difference is greater than 12. Anyway, if you look at the sample means, which are 86.7 and 77.8, the difference does not really exceed 12. It's just 8.9. So there really is no enough evidence to prove that the alternative hypothesis is true. Another example, let's identify what type of hypothesis testing to use. It is obviously a z-test on proportion because the parameters we see are proportions. That is 63 of 100 and 59 of 125. Convert them to proportions and we get 0.63 and 0.472 respectively. Those will be the p hat 1 and p hat 2. In this problem, the researcher wants to know if there is significant difference between the proportions. And if we just want to know if there is any difference, then that means the operator will be not equal to. Step 1, identify the hypothesis. The null would be their proportions are not different, and the alternative hypothesis will say that the researcher claims they are different. So their difference could not be equal to 0. Step 2, identifying the value needed to get the critical value, and that is the level of significance, which is 0.05, and the tail, which is two-tailed. Step 3, identify the critical regions, and the critical value from the left, that is positive. We're going to get the critical values on both sides. So that's going to be critical value from the left and from the right, and that is negative 1.96 and positive 1.96. Now sketching that will give us this distribution. Both sides are sketched, and if the test statistic enters either of those regions, then we reject the null hypothesis. In step 5, we solve the test statistic. Solve for the p-bar first, and that is just the proportion of the sum of 63 and 59 over the sum of the total sample sizes they came from. The result of the z calculated will be 2.36. It's positive, and it enters the positive rejection region. That means the conclusion would be the proportion of urban residents who favor the nuclear plant is significantly different to the proportion of suburban residents who do. We reject the null hypothesis. That means we can accept the alternative hypothesis. So they are significantly different. For the last example, let's try out the separate variance t-test. You may pause the video to truly understand the problem. It's quite long. There are many things to notice about this problem. First, it says the firm claims material X is lower than material Y. What I do to lessen the confusion moving forward to the next steps is to assign mu1 as the bigger parameter. If I believe that material Y would be the bigger average, then I will assign material 1 as mu1 and material X as mu2, and I will follow through with it for the rest of the steps. As you notice, I can translate this statement to material Y being greater than material X. Second thing to notice is that it did not state what type of t-test this is. Yes, the sample sizes are lesser than 30 and the sample statistic are averages, but it does not say if the variances or standard deviations are assumed equal or not. But there is a keyword that says two different road surfaces materials. Okay? In construction kasi class, especially in structures that are required to be very high quality because the safety of the public depends on it, tiny differences of materials matter greatly. How do we identify if materials are high quality? The easiest way to know that is that the standard deviation is low, or the strength or fatigue resistance has small standard deviation. You already know what standard deviation is, right? It is critical that in studies, the fatigue resistance is consistent. If it is consistent, then the standard deviation is lower. If it is not, it is bad quality. Okay, what does all of that mean? In this specific scenario, distinguishing their difference is important. So we assign this as separate variance t-tests. Also notice that their standard deviations are very different. For material X, which is made from recycled materials, the standard deviation is 150. While in material Y, the standard deviation is only 50. Now check out the formula. Unlike the pooled variance t-test, we are not solving the pooled variance. We do not have to solve a singular standard deviation because we are separating the variances here. But look at the lower part of this card. We see that we have to solve the degrees of freedom. We have to do that because their sample sizes and standard deviations are too far apart to just utilize the n-1 or the n1 minus n2 minus 2 formula. This formula will make sure our degrees of freedom for separate variance tests would make sense. Now let's go to the steps. Step 1, the hypothesis. The null would be that their difference would be equal to 0, but the alternative, their difference is more than 0. Notice that I assigned material y as the biggest number, therefore it is mu1, or the first one in the equations. Do that for the rest of the steps, especially in test statistic calculation. The bigger parameter goes first always. Step 2, get the values, and according to the problem, the significance is 0.01. It is right-tailed because the alternative hypothesis says greater than. And notice the calculation for degrees of freedom. Utilize the formula given a while ago, and it seems we must use 24. So you have to round it down. So your degrees of freedom here is 24. Given those values, you can now find your critical value from the table or from Google or from Excel, and that would be 2.4898. So sketch that out and solve the standardized test statistic, which would result to positive 1.3912. Since that number is outside the rejection region, then you should not reject the null hypothesis. That means there is no enough evidence to conclude that the average fatigue resistance of material Y is significantly greater than the average fatigue resistance of material X.